Alright guys, so as it says up at the top of the page here, we did right Riemann sums, left Riemann sums, midpoint Riemann sums. If you picture though what one of these graphs typically looks like, what actually ends up working the best is a trapezoid. So if we flip, for instance, I'm going to go back to the notes that we had when we were doing left and right. If we look at something like this, if we were to make a little trapezoid out of, like, let's say this piece right here, trapezoid takes this piece, connects it to this piece. There's very little difference between the actual area under the curve and what the trapezoid would look like. The only difference is that this piece right here is curved, and a trapezoid would obviously be a straight line connecting this endpoint to this endpoint. So trapezoid is going to be a very, very good approximation. The only thing that is going to be a little bit inaccurate is whether the graph is curved up or curved down. It could either be a little bit too high or a little bit too low. All right, so I'm going to write down, remember from geometry, the formula for a trapezoid. It's like this. So area of a trapezoid is 1/2, and then we say times the sum of the bases, and then times the height. Okay, so when we transfer that into working with some sort of table like we have below, what this ends up being, obviously, we're going to have 1/2 the whole time. The height that we're picturing, we're actually going to flip something on its side. So this is just a quick little visual of what a trapezoid would look like as the area under the curve. So if we chop up like this, we actually use this as the height and then these as the bases. So you've really got to kind of picture a traditional trapezoid on its side like that. So it's not really height, it's more like width, and so that's going to end up being the length of the interval. All right, so this measurement right here will be the width of the interval. Okay, this will be the left and right y value. The left y value, the right y value, or whatever values you're pulling off a table, you know, things like that. So we add them together. So basically what ends up happening is we add them together and then average them out. So what the trapezoid rule ends up actually being is the average of the left and right. So it's like taking the best of both and averaging them out. So you end up somewhere right in the middle. All right, so this example that we're going to look at, this first one right here, we've got this whole table of measurements, rainfall in inches per hour during a 10-hour thunderstorm. We're going to approximate what the total rainfall would be. So I'm going to show you exactly how this would be set up. So a 10-hour thunderstorm, we are going to have all of these intervals right here. So we've got these 10 intervals, so you are really going to get a good look at what the trapezoid rule should look like. All right, so this first interval right here, every single one of these is going to have a piece like this. So you're going to have 1/2 on the outside. Remember what that ends up doing is averaging the two together. Sum of the bases really ends up being sum of the two values from the table. And then times the height. Remember, h in this formula actually ends up being the width of the interval. It's a 10-hour thunderstorm. They're being measured every hour. So the length of this interval would be 1 hour. All right, so we're going to keep going. We're going to do this for every single one of these intervals. So then we move to this second interval right here. We average out these two values in the table and then multiply by the length of the interval. Plus, and we're just going to keep this pattern going. So average out the 0.49 and the 0.32 times 1 hour. Next from 0.32 to 0.3, another hour. Now it is of course possible that the time intervals could be uneven, and if that was the case then they would tell you exactly what the time intervals were. You'd see more like an XY style table. Okay, so next one takes us from 0.3 to 0.23. .23 to 0.09. Oops. 0.09, 0.8. From 0.08 to 0.05. I just realized I said 0.8. I did write 0.08. I promise that's right. Plus, almost done here. 0.05 to 0.11. And our last trapezoid goes from 0.11 to 0.12. Okay, so we've got all that written out. Whenever these pop up on the AP test, I promise you they will tell you that you have to show all of your work. Okay, so all of that has to be all written out perfectly. So let's sum these all together. Of course, my calculator is not loading. I might just pull my phone out. Oh, good, operating system. Yep, gonna pull my phone out. Okay, so let me show you just a quick little trick here. Since for these ones, they're all the same interval, and they're all being multiplied by 1/2. So I'm just going to do the 1/2 and the 1 at the end, and I'm going to just sum all these together first. All right, so I'm going to take 0 plus 0.41 Okay, so that's the sum of all of these, and then they're all being multiplied by 1/2. They're all being multiplied by 1. I don't have to do that. So I'm going to divide everything by 2, and that is what we end up with. 2.14, so that would be our approximation. So we get 2.14, and then when you're doing units, remember 1/2 doesn't have a unit attached. These are all inches per hour, and then times hour. So what we end up with is inches. So over that 10-hour time span, we've got a total of about 2.14 inches. All right, I want to squeeze something in just to show you. Actually, I can squeeze it in on the next page. All right, so let's do these problems really quickly, at least the first one. Maybe we'll save the second one and do together. So we've got this table. This is what I was talking about here. We've got not necessarily equal intervals, so they give you the x and the y. And so it says use a trapezoidal sum with the 4 subintervals indicated by the data in the table to approximate the area of the cross-section of the river at Picnic Point. Okay, so we are going to sum all of this up here. So we've got 1, 2, 3, 4 intervals. They're not of equal length, so that becomes super important to use the formula carefully. So for the first subinterval, we're going to go 1/2. That's just part of the formula. Add the 2 depths together. So 0 plus 7, and then multiply by the length of the interval, which is from 0 to 8. Plus, and then the next trapezoid, add the 2 together. 7 and 8 would be the 2 depths, and then the width of this interval would be 6 feet wide. Plus 1/2 is just from the formula. Then for these two, we use 8 and 2, so we can average out those 2 depths. And then this is an 8-foot interval. Plus 1/2 from the formula, average out these 2 depths, and then the length of this interval is just 2 feet. Okay, so we would add all of those together, and then just for fun, we're going to do this by hand because this is question 3, which means it's on the non-calculator portion of the exam, so just for fun. So 1/2 times 8 gives us 4, and then 4 times 7 is 28, plus 1/2 times 6 is 3, 7 plus 8 is 15. 3 times 15 is 45. Plus 1/2 times 8 is 4. 8 plus 2 is 10. Plus 1/2 times 2 is 1. 2 times 0 is 2. Okay, so let's add these all up piece by piece. So 28 plus 2 is 30. 45 plus 40 is 85. And one more round gives us 115. All right, so these were in feet, these were in feet, so when you multiply everything together, what you actually get is feet squared, which makes sense because it says the area of the cross-section. So you're going like feet in one dimension and then feet deep, and so the cross-section you would get is in feet squared. They did tell you that here. All right, so that would be your final answer. All right, one thing that I want to just kind of throw up at the top here, a little bit of extra information, whether a trapezoid rule is an underestimate or an overestimate, and this actually depends on concavity. So we're going to take, like a right side up parabola like that and an upside down parabola like that. So if we make even just, 2 trapezoids in here, what you will see is that the trapezoid goes like this, and it's just over a concave up curve. So if it's concave up, this is an overestimate. So if you're measuring on a concave up curve, you have an overestimate. Concave down curve, same thing. If we make even just two trapezoids here, when you connect the dots on the trapezoid, it ends up going just under the concave down curve. So if you've got something that's concave down, you end up with an underestimate. So if you guys remember with the left and right Riemann sums, under and overestimate were determined by whether the function was increasing or decreasing. With the trapezoid rule, it's determined by whether the function is concave up or concave down, as to whether the trapezoid would go just under the curve or just over the curve. All right, so we'll save that last AP problem to do together.